All right, and then before we get started with our next session, I'd like to share our first soil fact of the event as promised. So did you know that about 95% of our food comes directly or indirectly from soil? Every bite we take is a quiet reminder that without healthy soil, feeding the world becomes nearly impossible. So something to just think on when you're taking your next bite. All right, so for session 2, this next session will highlight SDSU's faculty and SDSU researchers' work on sustainability within the research space and classroom. Faculty and student researchers will present innovative projects and course designs that address pressing environmental challenges through diverse academic lenses, from STEM to humanities. Stay tuned to learn how research and teaching can intersect to inspire climate literacy and community engagement across all fields of study. And again, if questions are not answered during today's presentation, event organizers and speakers will follow up following the event. So now over to our session moderator, Dr. Ariel Levine. Thank you. Give a round of applause.
So we click on this thing right here. Okay. All right, thank you so much. All right, well, hello, everybody. One of the exciting aspects of SDSU is the extensive sustainability-related research taking place at the university. We have faculty across numerous departments working to understand and address issues such as plastic pollution, increased fire frequency, climate change, ocean and coastal sustainability, sustainable agriculture and food systems, and more. And today we are fortunate to have 3 faculty members talk about their research projects related to sustainable water use in agriculture in California. So first we'll hear from Natalie Mladenov. Dr. Natalie Mladenov is a professor of environmental engineering. She directs the Water Innovation and Reuse Laboratory, which investigates pollutant mobilization, fate, transport, and treatment in natural and engineered systems. Dr. Mladenov's research and teaching is motivated by the need for sustainable management of water resources in the face of water scarcity, and focuses on the biogeochemical and photochemical processes that affect contaminants of concern in water. And Dr. Mladenov will be presenting today about her research group's work looking at the health of the Tijuana River, how this has changed over time, and options for a sustainable future for mitigating pollution in the river. Next, we'll hear from Dr. Matt Weingarten. Dr. Weingarten is an associate professor in the Department of Earth and Environmental Science. His group uses computational models to explore both water and earthquake problems. He received his Bachelor's of Science in Geology and Geophysics from the University of Wisconsin-Madison in 2009, and a PhD in Geology in 2015 from the University of Colorado, Boulder. Dr. Weingarten will present his research group's work on mapping groundwater depletion for agriculture in California's Central Valley and the implications for future sustainability. And finally, we will hear from Trent Briggs. Dr. Briggs is a hydrologist and a geographer with research interests in the impacts of land use on hydrology, water quality, and sediment. Dr. Briggs and his students use satellite imagery, fieldwork, and modeling to diagnose and analyze water-related problems that impact the environment and human welfare. His field locations include American Samoa, southern India, the Himalaya, and the US-Mexico border region. Most recently, he and a team of collaborators and students have analyzed heat stress in farm workers in the Imperial Valley. Dr. Briggs will present on this work to understand and mitigate farm worker heat stress. And just as a reminder, the QR code showed at the beginning is where you can submit questions, and we'll save all of our questions after the 3 speakers have completed their presentations. So, Natalie?
All right, just getting a handle here. Okay, hello everyone. Thank you, first of all, Ariel, for that introduction, and to the organizers of this event for having me here. I'm really really happy to be here to talk to you all and to start things off on this session talking about the Tijuana River, which is a contentious topic, but a really important one for our region. So if you've lived here any time at all, any length of time at all, you've probably heard about Tijuana River pollution, seen the news about sewage pollution coming across the border, and the inability to stop that flow, continuous cross-border flow, resulting in real impacts to our South Bay, in particular to the city of Imperial Beach and to Coronado Island and our coasts. And that's a public health issue as well as an environmental health issue with more than 1,000 consecutive days of beach closure, and those are real impacts, both public health and economic, to the region. Let me just, for the sake of time, move to the last notice here. This is from the Good Neighbor Environmental Board report. This is to the President and Congress. It's led by our very own Paul Ganster in geography, and they write in this report, the pollution crisis from the Tijuana River is not just an inconvenience, it's a public health emergency. And so nothing could be more true. So what do we know about this problem and about the Tijuana River quality? So I'm going to talk a little bit about that today. How has it changed over the years? What is the way forward what are we doing right now to address the issue? And what is one option for perhaps a more sustainable way forward? Okay, so in this part of my presentation, I want to acknowledge that there's been a lot of work done here at SDSU by different faculty members, also by other universities in the region and around the country. But right here at SDSU, we've really looked at this issue of Tijuana River pollution from as far back as the 80s with the work of Rick Gersberg in public health, looking at metal pollution, the work of Rick again and Carrie Sant and Scott Kelly, myself and Matt Verbilla looking at pathogens, microbial pollution, hepatitis A, SARS-CoV-2 in the water, work by Paula Stiegler-Granados in public health in collaboration with Unha Ho and Kim Prather at UCSD, looking at that, not just the water pollution, but the water to air transfer of pollution. And work by our very own Trent Briggs here, looking at sediment pollution and trash. And these are numerous pollutants in the Tijuana River that we've been all studying. So we have a good handle on just how bad it is. Paul Ganster in Department of Geography also worked on or led this Tijuana River Watershed Atlas that has been a real fundamental piece of work for driving change and has worked on binational cooperation to address this problem with our colleagues across the border, policymakers, and so on. And then we've also been looking at monitoring the situation in real time, and I'm going to talk about that briefly today too. And that's a collaboration with Trent Briggs and Dan Sousa and myself on this topic. So this is not a new issue. In fact, we've been struggling with pollution in the Tijuana River coming across the border for about 90 years. So this is a long-term issue. This photo was taken in 1937. And you can see in 1934 is when we started to have the first cooperation on the topic. I want to point out in 1994, the International Water or Wastewater Treatment Plant was constructed to handle the flows and treat that wastewater coming across the border, but it is unfortunately quite undersized. And now we have some new investment as of the USMCA agreement to expand and upgrade those facilities with hundreds of millions of dollars of funding to address those infrastructure deficiencies, both in the US and in Mexico, in Tijuana. So with our sensors and our real-time monitoring, we potentially can track, hopefully, the progress that comes as a result of those investments. This is an image from a recent magazine article that showcased the work that we've been doing with the real-time sensors. And I'm just going to talk quickly about the sensor work because I want to get to something else after that. But so we've been working with sensor platform that's located in the Tijuana River estuary. analyzing the water in the lab to ground truth our sensor platform data to verify it. And we've seen that our sensor data actually can really distinguish between times when we have intermittent flow, so back in 2021 when we didn't have continuous cross-border flow, but instead we had intermittent rain events that resulted in cross-border events, versus this 2 years or more of constant cross-border flow. So without getting into the details of how the sensors work, you can kind of see there the difference in background levels and then what results from the continuous cross-border flow. So real-time sensors are able to distinguish the poor water quality from better water quality. So hopefully in the future we can get back to a time where we have, improved water quality, and we can detect that with our sensor platform. We're also able to see how tides influence the water quality. And again, I'm going to skip over this for now. What we see with our sensor platform, zooming into, the real-time data is very, we can get to a really refined scale and look on a daily basis or even on a minute basis and see some real changes. The most severe water pollution occurs during low tide in the estuary, and also the estuary experiences a spring tide and neap tide conditions, and neap tides result in the worst water quality, especially in the surface layer. All right, so our work also, as I said before, has the potential to monitor recovery. So now that we have the sensor platform, we can see if these investments, $600 million to expand and improve the infrastructure of the international treatment plant and different sewer lines and another treatment plant in Tijuana. So our work can evaluate the current worst case condition, and then we can use the sensor platform to evaluate the effectiveness of those investments. So this is a great way forward. We need these investments desperately. We need to improve and upgrade these facilities. But since this has been happening since the 30s, right, we have this current solution, but what could be a more sustainable way forward? And I think to do that, we need to look at the watershed hydrology of the region and really understand how water is moving, how are these pollutants moving through the watershed. So here's a map or aerial image, and you can see San Diego and Tijuana. And I'm going to overlay on that one of the maps from the atlas. So just kind of pop that on top. That is the Tijuana River watershed. And in dark brown, you can see the higher elevation areas. In green, those are the low-lying areas. And water, as we know, is always going to flow. Unless we engineer it to do otherwise, it's going to flow downhill. And it's going to, no matter what engineered solution we put in, it's always going to come across the border and go exit via the Tijuana River estuary there at the mouth of the Tijuana River. Okay, so engineers like myself worked to modify that, to deal with the sewage pollution. So we have the PBCLA pump station. This is a huge pump station. It pumps water from the sewage collectors in Tijuana and from the Tijuana River, and it pumps it up to our treatment plant located on the US side of the border, which we are required by treaty to treat that water coming from Mexico. So many people don't know that, but the US is required to do that treatment. And also pumps that water to another treatment plant in the southern part of Tijuana. Okay, so when that pump station is working well, things go well, and we get treated wastewater discharged to the ocean. So that is what we're hoping for with these investments, that we have not had treated water going to the ocean. It has been untreated wastewater, but with these upgrades, we will start having improvements in treated water going to the ocean. But keep in mind, that's a lot of water. That in total is about, on average, 70 million gallons per day. That's the size of a really large treatment plant in LA or San Diego. Okay, so that's a lot of water. And that's going to the ocean, fairly good quality. Now, what can cause an issue? So I've put this three-headed monster here, the Cerberus dog, which is really the crux of our problem in the Tijuana River. It's not just sewage, but we also have sediment and trash flowing down the Tijuana River. And you can imagine what happens when sediment and trash go into these pump stations and other infrastructure. It can clog the pumps and the turbines and be very destructive. And then that's hundreds of thousands of dollars to replace, or maybe tens of thousands to repair, and many months while we're waiting for that to happen. So how did that sediment transport and trash transport happen? Well, we do have the expert in that here, Trent is here. But it does come down to the rapid population growth that's happened in Tijuana. And we're not the only ones looking at this. Our colleagues across the border have been studying this phenomenon as well. When we have rapid urban growth, we deforest the landscape, and there's less stable vegetation to hold that soil. So then you have a lot of erosion. And our landscape already in Tijuana is very erosive soils. So you end up with soil erosion, but even worse, you can have loss of property, loss of life in these landslides. So what's a sustainable way forward? So as I mentioned, our colleagues in Tijuana at El Colegio de la Frontera Norte, Lina Ojeda Reva is an author on one of the chapters in this book on sustainable development at the northern border. And she talks about urban greening as a way forward. So just imagine, and I steal this graph or this figure here from from Watersheds Canada, but it applies here too, right? So planting native vegetation with its deep-rooted systems can hold that soil back. We know that. That's been studied for a long time. It can therefore slow erosion, promote infiltration, reduce flash flooding, and also to some extent capture trash and plastic, as well as the many other public health benefits you get from urban green spaces. And Lina Ojeda Reva, professor at COLEF, talks about how there's such a low density of green spaces in Tijuana. It's well below the World Health Organization recommendations for urban green spaces. Okay, so how can we want this, we see this as a sustainable way to address the sediment issue, but how are we going to water all of those urban green spaces? Well, remember, in Tijuana, we have a lot of wastewater. That flows via arroyos and ends up in storm drains, ends up in the Tijuana River. So with my colleagues also at El Colegio, Gabriela Munoz Melendez, Armando Arteaga, Lina Ojeda Reva, we studied the way of decentralized wastewater treatment to provide water for urban greening, for greening urban areas. And there is a great example of this. COLEF has been running Ecoparque. Maybe some of you have heard about Ecoparque. It's an amazing, small, decentralized wastewater treatment plant. They provide urban greening. You can see in 1988, what the site looked like, and then 10 years later, in 1998, you have this huge swath of green land that is going to be stable and protected from erosion. Now just imagine these green, urban green spaces fed by decentralized wastewater treatment scattered across Tijuana. That would be wonderful. However, there are some issues with that, some socio-political challenges to decentralized wastewater treatment. No time to talk about that right now, but there are still these great examples, Ecoparque, and there's another one in Tecate, the Tres Estrellas facility in Tecate. So they've shown that this is possible. It will require maintenance. It's not a hands-off approach, but it is doable. Okay, so let's say we see a larger water treatment scheme as a better way to bring more water to Tijuana. Well, we can do that as well. Remember, we have the International Wastewater Treatment Plant that's treating 50 million gallons per day and more than that when there's a storm event. So with my students in my ENVE 647 class, grad class on physical chemical processes for water pollution control, the students have been designing advanced treatment, so to take that treated wastewater and treat it even further so that we can use it for landscape irrigation. What ends up happening? Well, we have enough water If we treat 50 million gallons per day, we have enough water to water 150 square miles. So that's almost half of Tijuana's 340 square mile municipal area. So we can do it with small decentralized projects, we can do it with large centralized projects, and there are certainly logistical and legal challenges with getting that water back across the border, but I think those can be overcome. So to recap, maintenance of infrastructure will always be a challenge. There will always be failures, and there might not be the funds to repair at that time. So we need to look not just at solving the problem, kind of the Band-Aid approach, but also looking at the source of the problem. And urban greening is not the only solution, but it's one of several that can really help address the problem, providing the green spaces and using both centralized and decentralized treatment to provide that water, and also address the wastewater, the volume of wastewater that's also needs to be treated in Tijuana. So I hope I've convinced you that there are positive ways forward for this problem. So thank you for your attention, and happy to turn it over. Just made it.
All right, thank you so much, Natalie. A reminder to save your questions for the end, but you can enter them to the Google form now. And next we'll hear from Matt Weingarten.
Hi, everybody. Today I'm going to talk a little bit, I'm going to move us from talking a lot about surface water to talking about groundwater, and specifically modeling groundwater depletion in California's Central Valley, which is a few hundred miles north of where we are right now. The motivation for modeling groundwater depletion, there are a number of reasons for this. But there are practical economic reasons as well. California has a $59 billion agricultural industry. We are the #1 agricultural state in the United States. You might have thought it was Indiana or Iowa, but no, it's California. We grow 100% of the nation's almonds. We grow 40% of the nation's fruits and nuts. Most of that is grown in California's Central Valley. Now you see a picture here of California's Central Valley with this nice, what looks to be a river. That is an engineered structure called the California Aqueduct. That brings millions of acre feet of water per year from the northern part of California to the southern part of California, mostly in the Central Valley, but also to cities like Los Angeles and the neighboring communities there. So a whole heck of a lot of the agriculture that's done in the Central Valley uses surface water via engineered structures. But before that surface water infrastructure was built, virtually all of this region was either semi-arid or arid and was irrigated using groundwater pumping. Now, in the most recent time, maybe 10 or 20 years, the conflicts over water, namely surface water in California, have grown. And in times of drought, we typically tap groundwater resources because groundwater is sort of like the savings account that you tap into when your income sort of starts to, your annual income starts to go down. This aquifer beneath the Central Valley it counts for 20% of all of US groundwater pumping. It's the second most pumped groundwater aquifer in the country, behind the Ogallala Aquifer in the central part of the United States. Now, we've been pumping the Central Valley Aquifer since the late 1800s, so the aquifer's been widely depleted even before the adequate surface water supplies and the expansion to sort of modern day extent of California agricultural dominance across the United States. Particularly here in the southern part of the San Joaquin Valley, so there are two sort of subbasins, well, there are three subbasins within the Central Valley. In the north, you have the Sacramento Valley. In the south, you have the San Joaquin Valley. Cities like Bakersfield and Fresno here, if you're familiar, if you've driven from Los Angeles to San Francisco on Highway 5, you've driven actually right past that California Aqueduct on the western side of the Central Valley here. And in the very southern part of the Central Valley is the Tulare Basin. They've been pumping the shallow aquifer since the late 1800s, and by the 1960s, so over about a 60-year period, due to a lack of management, groundwater levels had already been depleted by upwards of 400 feet. That would be equivalent to about a 30-story tall building, turned on its head, and water levels are dropping from the base of the building to the top of the building, basically, okay? So this is a huge groundwater level decline. In addition to the groundwater level decline, there's also been a whole heck of a lot of land subsidence related to this groundwater depletion, okay? So that's the sort of motivation and the sort of setting for why we're interested in trying to understand future groundwater depletion if maybe under changing climate, drought is going to be more and more prevalent and potentially more extreme. So about a little over 10 years ago now, it's amazing to think about that this act was passed 10 years ago. The government of California and the governor at the time, Jerry Brown, started to realize that groundwater was not recharging as fast as it was being used, especially during this couple-year drought period leading up to the passage of this law. And so he and the lawmakers at the time passed what's called the Sustainable Groundwater Management Act. Prior to the passing of this act, there were essentially no groundwater regulations in California. If you owned a piece of land and you could afford to drill a well, you could pump as much groundwater as you could get out of that well, and you didn't have to tell anybody how much you pumped or where you were pumping. So it made things a little bit difficult to try to understand what was going on at a regional scale when no one was sort of saying how much they were pumping. We just sort of had to watch this anecdotally, almost. So the goal of this law was to start to set up some sort of framework to monitor and also plan for a long-term future with groundwater resources. So the goal here is to essentially force Central Valley Aquifer partners to come up with groundwater sustainability plans, or GSPs. They did that over the last 10 years or so, and they're now just in the beginning part of what's called the implementation phase of their groundwater sustainability plan. So for the next 20 years, they're going to be figuring out how do we get to sustainability. By 2040, we'll have achieved sustainability, and we're going to maintain that sustainability by up until 2070. The three main questions that I'm going to address in today's talk are: where are the areas of greatest long-term sustainability concern? I'm not going to get too much into this, but how will the law's political boundaries, which are in conflict with the aquifer itself, meaning the aquifer is bigger than the sort of piecemeal political boundaries that make up the groundwater sustainability plans. And then finally, how drastic is depletion expected to be in more poorly monitored regions? We can answer all of these questions, or some of the portions of these questions with some of the work that we're going to do here with modeling. So first I want to address what the sort of goal sustainability means in the context of groundwater. And we're going to be specifically focused on the 20 critically overdrafted aquifers here in the southern part of the Central Valley, in the southern San Joaquin Valley. What I'm going to show you today is essentially a bunch of modeling results that show you whether or not we're going to be able to meet our sustainability goals. So this is an example of one indicator well. So there are about 1,000 indicator wells, all monitoring groundwater levels, spread throughout this region. And they have a historical drawdown, right? That's just shown in the blue dots here, drawing down the water levels. Here we are in 2020, obviously that's 5 years ago, but you can imagine this is the case today. And in theory, over the next 15 or 20 years, we're going to be raising groundwater levels to what's called a measurable objective water level target, basically something that's above the current water levels, right? We're trying to achieve something where water levels are rising. A secondary water level is called the minimum threshold water level. This is the water level that's usually below the current water levels that would absolutely be the worst case scenario for sustainability. It would be the water level drops below the bottom of the well and you can no longer pump it, et cetera, okay? So we don't want minimum thresholds, we want measurable objectives. So what we're gonna do in this study is compile an indicator well database. So you have to imagine that, well, there are tens of thousands of pages of consulting reports that have been filed over the last 5 years that represent the groundwater sustainability plans for the various regions in this area. We sifted through those documents and compiled the regional data set of indicator wells so we could use a groundwater model to see how well they're going to meet these measurable objectives and minimum thresholds. And we'll use the combination of those two to evaluate sustainability. So when we put together our indicator well database, and there are actually two different aquifers in the Central Valley. There's an upper aquifer, the shallow aquifer, and there's a deeper aquifer called the lower aquifer. And they're treated differently by these groundwater sustainability plans. For the purposes of what we're talking about today, I'll just briefly mention the differences between the two. In the upper aquifer, you'll see that there are a lot more monitoring wells. And particularly places like counties like Kauai, Kings, and Tulare Lake have good distributions of indicator well density, right? You want to have as many wells monitoring water levels as possible, in theory, because the groundwater levels are drawing down over a large 3D space, so we want to have as many monitoring wells as possible to measure that. Some areas have very few monitoring wells, like Merced. In fact, Chowchilla doesn't have any official monitoring wells, and you can see that some of the areas with the largest depletions, right, in the southern part of the Central Valley, like Kern County, have relatively few in the shallow aquifer. In the deeper aquifer, we have 312 wells, and you can see that the monitoring's better in Kern County, but it's substantially less in Modesto, Turlock, Merced, and Delta Mendota. In fact, one thing that we realized after making this database is there's really not an accepted well density of sustainability monitoring that's been published in the academic literature. There's sort of stuff in the GSPs that's sort of self-referencing each other, but there's not really a guideline for what the density should be. In fact, I think it's somewhat subjective based on how much depletion there actually is in a certain area and what the geology of that area is. So now we're going to take that well database and we're going to build and compare it with a hydrologic model. And fortunately, we were able to use an existing historical state-of-the-art model called the Central Valley Hydrologic Model, built by the U.S. Geological Survey over here in Point Loma at the California Water Science Center here in San Diego. This was created to aid water managers, and it simulates water budgets from 1961 to 2019. So it was set up perfectly for us to take this model and extend it into the future. It incorporates all sorts of stuff: lithology, hydrology, water consumption, land use, surface water. It is a fully calibrated model. It's perfect for us to sort of use to extend into the future. So what I'm going to show you here is a baseline hydrologic model. What this baseline model means is we're going to take the current distribution of land use, all the almonds and fruits and nuts and cotton that's grown here in the Central Valley, and we're going to assume that those are the farms that stay using water from 2020 to 2040. At the same time, we're also going to assume that they're going to pump the same amount from 2020 to 2040, and this is what the upper aquifer drawdown would look like in space in 2040. So in these areas of gray, you have between 0 and 5 meters of drawdown. In the areas of like light pink, you have between 5 and 10 meters of drawdown. And then in these areas of darker pink, you have up to 20 meters of drawdown, which is about 60 feet. Some areas, like in the southern part of Kern County, or in the western part of Kern County, are actually having water level rise, and that's because they are doing managed aquifer recharge in that area. So that's a good thing. So we actually are showing that that's having a positive effect. Okay? If you extend this model into 2070, you start to see how continuous pumping at current levels sort of draws down the water levels over large areas, and the depletion gets more intense and more interconnected. The depletion is most pronounced along the west side and in the northern part of Kern County and Tulare Lake area. And there are also other regions as well. This drawdown is not a good thing. Obviously, we want water levels to be rising. But how does that compare to the actual sustainability targets set by the various GSPs, the dozens and dozens of GSPs that have been made for the various areas within this region? Well, let me show you one example of one sustainability indicator well as compared to the modeling results that I just showed you. So here's an example of a measurable objective and a minimum threshold water level set for well 863. And here is the modeled groundwater levels from our groundwater model depletion from 2020 at 0 to minus almost 30 meters. This well, based on the sustainability targets set by this GSP, would be sustainable because it's not dropped below its measurable objective. And this is, I just make this point to highlight the fact that sustainability is subjective, okay? This is a very conservative goal, and they've met their very conservative goal despite the fact that the water level is modeled to drop by close to 100 feet, okay? All right, there are other examples of this spread out through the indicator well database. Some counties and some areas have set very aggressive goals and will fail to meet their goals because they've set them so aggressively, not because they have a lot of depletion. Okay, so when you look at the whole picture altogether, and I know this is a very busy plot, I'll just highlight a couple things. Green dots on this map show sustainability is met, okay, both for measurable objective and minimum threshold. Yellow dots on this map mean they failed to meet their measurable objective, but they met their minimum threshold. And then orange dots mean that they failed both. And you can see that the highest passage rates are happening in this area of Kauai and in Thule. It's quite hard to see the association between where model depletion is happening and where passage is actually happening, okay? And that's because of the heterogeneity and how the goals are set between the various plans. Again, some are very conservative and some are very aggressive. So it really depends on how the goals are set. In all, we found that under a baseline scenario, close to 50% of the wells in 2040 will fail to meet their measurable objective. Basically, 1 out of every 2 wells will fail to meet their measurable objective. We ran various scenarios of pumping into the future. You can imagine this as sort of a drier climate, long-term drought conditions. A 50% increase in pumping would result in much higher rates of well failure. A sustainability indicator well failure. We don't expect that to be the case into the future, but we ran this as an example model. If you run the opposite case, 50% decrease in pumping, you see that water levels are rising nearly everywhere. This would be a catastrophic thing for agriculture in the Central Valley to decrease pumping by 50% for the next 20 years. And even if they did this, 30% of the measurable objectives would be failed to be met. So these are the areas where those wells, that 30% are the wells that are being set very aggressively. The measurable objectives are very high. So in sum, we showed a couple different things that basically under baseline conditions, 1 out of every 2 wells will fail to meet their measurable objective by 2040. Not a good thing. And even if we decreased our pumping by 50%, some of the areas where the wells are set, the sustainability indicators wells are set very aggressively will fail to meet their goals. And I just want to acknowledge that this is a team effort between me and a number of my students, both undergraduate and master's students. Several master's theses and undergraduate theses have come out of this project, and yeah, they're shown here. Thanks very much.
So hi everybody. I'm the last speaker before lunch when we're talking about food, so we're all getting hungry. So with that in mind, I'll try and keep it relatively short. So I'll be talking about one aspect of irrigated systems that we often neglect to think about, which is the farm working community and the heat stress that farm working community experiences, and with a focus on the Imperial Valley. And this is a collaborative project between especially the School of Public Health, who has done a lot of the field work for what I'm going to show today. So 2 million farm workers in the US, they're 20 to 35 times more likely to die from heat than other workers, right? Very vulnerable group. There's been 151 farm worker deaths in California between 2005 and 2021, and they have higher injury rates and kidney disease as a result of heat exposure. Within California, there's a hotspot of heat-related illness. This map is the rate of heat-related illness per 100,000 workers from 2000 to 2017. And the Imperial Valley stands out. It's just an hour and a half east of here. And the right inset map shows the Salton Sea and the Imperial Valley, which is where the focus of this work is. And one might ask, how does a hydrologist get involved with farm worker heat stress? I started working on water conservation and water balance modeling in the Imperial Valley, which also impacts the near surface climate. So when you irrigate a landscape, it impacts it typically decreases the surface temperature, the air temperature, and increases relative humidity. Both of those impact farm worker heat stress. And so I became aware of the issue of heat stress through talking with colleagues and from listening to the news, and thought that we might be able to apply some of our techniques to map surface climate and then look at the implications for heat stress in farm workers. So I guess if I had a sort of career advice, be flexible, right? Think widely about the kinds of problems you want to look at. And often you can find creative ways to engage with a lot of different topics in the sustainability field. So the title of the project is Mapping Trends in Rural Heat Stress and Co-Production of Knowledge on Heat Stress with the Farm Worker Communities. We knew that in order to have any kind of valid understanding of heat, we had to talk with the people who are actually impacted. And so we have three questions. When and where are workers exposed to heat? And that's where this sort of climate modeling and remote sensing component comes in. Secondly, the public health people talked with the farm workers and they instrumented them with sensors to measure their physiological and personal experiences of heat. And then what data is useful? What can we do to mitigate mitigating heat stress, and how can we best disseminate it for effective action? And so the gold standard, you might think air temperature, that's the most important thing. Turns out that's not the most important thing. So we use something called the wet bulb globe temperature, which integrates the dry air temperature on the left, the natural wet bulb temperature, which is impacted by relative humidity, and the black globe temperature, which is impacted by solar radiation. Right, so the little equation there, you might notice that the wet bulb temperature gets 70% of the weight. So how humid it is really important. The air temperature only gets like 10% of the weight, and the black globe temperature, which reflects solar radiation, gets 20% of the weight. So we can calculate this kind of index with a global climate model, and we can then determine when and where our farm workers are exposed to high levels of wet bulb globe temperature. Okay, so we might think, oh, we can just map wet bulb globe temperature and then we'll know the answer. Well, it turns out we have to understand where and when farmers are actually in the field to intersect with our climate model, because we'll have data for hourly for every day of the year. We need to know, are they working at night? Are they working during the day? So turns out that a lot of farm work is done at night. And that's not necessarily primarily to avoid heat stress for the farm workers. It avoids heat stress in the plants. So the plants are at maximum turgor and maximum sort of freshness at night when they're recovering from wilting during the day. So some crops you can illuminate with huge stadium lights, and the farm workers can work in the field at night. There are other reasons why they don't like to do that, because they have childcare issues and safety issues. But there are a fair amount of operations that happen at night where the heat stress risk is much less. But there are some crops that you can illuminate with huge stadium lights, like dates. And so it becomes too complicated. There's shadows all over the place, it's a mess. So those kind of crops have to be harvested during the daytime. And they're also harvested during the hottest months of the year. So often when we think of, or at least my own imagination of what farm workers are doing is working a lot of these low-lying crops, like high-value crops like lettuce, baby greens, those kinds of things. A lot of those are actually harvested at night. And the big heat stress risks are associated with some of these tree and nut crops that Matt was talking about earlier. And so we can do things like plot a time series. So the top starts in April 13th and it ends on October 25th. And then the vertical axis is the hours of the day. So night is at top, so midnight, and then about halfway down is noon, and then at all the way bottom is nighttime again. And by talking with the farm workers and interviewing them and their community partners, we've been able to map when are key periods of activity, both in terms of what date they're happening on. Do they happen in April, May, June, July, August, September, October? And do they happen at night or during the daytime? And so we've been able to find, and then overlaid on top of that is the wet bulb glow temperature threshold. So pink means we basically shouldn't be working at all, and the yellow and the white means that you're relatively safe if you're working at a moderate pace and have no other health issues. Key caveat. And so grape harvest, for example, has some potential problems with heat risk. Dates, as I mentioned before, another unexpected finding was that there's a lot of land preparation that goes on during the summer. So we think, oh, well, they're harvesting. That's when everybody's actually working in the fields. It turns out there's a lot of land prep that goes in during the summer. And so, we're able to identify the specific activities that we really need to be alert for. I'm going to skip that in the interest of time. So the second question is, what are the farm worker experiences of stress? And in order to answer that question, Nicholas Lopez Galvez in the Department of Public Health has great working relationships with our community partner there, and is instrumenting farm workers with sensors that monitor their skin temperature and their heart rate. And so they'll work in the field while the sensor is collecting data. And this is just an example of one working day. So it starts at about 6 in the morning, sorry for the small fonts. Starts at about 6 o'clock in the morning and he ends at 2 in the afternoon. And on the y-axis is the skin temperature. And about halfway up, let me see if I can do this without, let's see, laser pointer, this one? Yeah, so here's lunchtime. And the 37 degrees is 98.6 Fahrenheit, right? So if you're above that, and if your skin temperature is higher than 98.6, you're not cooling off to a healthy level. And so one thing that we're noticing is the skin temperature goes up throughout the entire work period. It doesn't go down very much during lunch, and it keeps going up to unhealthy levels in the afternoon. And we're using these kind of data to understand if the existing regulations are protective of farm workers or not. The other thing that the public health group did was interview farm workers, and they found some fascinating things. And I don't care what part of the sustainability matrix you're a part of, if you're a physical scientist, if you're a social scientist or whatever, talk with people who are directly impacted, because we learn so much. So one thing that we found that gives us some hope for addressing the issue is that most farm workers are accessing climate information on their cell phones. They have smartphones. They access weather apps, and we're working with them to identify better exactly what kinds of apps they're using. They also follow the lead. Who's the key decision makers? The workers follow the lead of their managers, so the person who's in the field with them, managing the work for reducing their stress during times, reducing their hours during periods of heat. So those are really the key decision makers. It's people in the field who are actually going to make the real-time audible calls. And then managers can end a workday after 6 hours if it's too hot, and we've seen that happen a lot. But it's based on how it feels, right? It's a very subjective kind of feeling, and there's a lot of information in that subjective feeling, but we also think that those decisions could benefit by having access to information about the wet bulb globe temperature. Because in California, our heat regulations are based on air temperature only. And so we suspect that is not protective of the workers. And that we have another paper comparing California's policy with the National Weather Service recommendations, and they suggest that farm workers are not getting nearly enough rest breaks to keep them out of heat stress trouble, even if the law is being strictly adhered to. So one other very perhaps sobering but also relevant thing that we found was that the farm workers have never seen anybody besides their managers come and check on heat stuff, right? So they've never seen anybody from the county or the state, public health, nothing, to come and check on them, and that's due to labor constraints. I mean, there's just not the workforce in the government and regulatory community to be checking on people, but we were also surprised to hear that nobody had actually seen anyone. So the take-home message is that the decision-making is really in the hands of the farm workers themselves. They can take breaks, and in the hands of their direct managers. And so one thing that we're testing now is a mobile app that's put out by the American Industrial Hygienists Association, and it gives you a WGBT and forecast, both nowcast and forecast, and you can put in what kind of clothes you're wearing, you can put your activity level, and it's available in Spanish. And so at the end of May this year, we're going to do a field test and determine whether it's usable by the workers, if there's any modifications necessary. One other thing we learned is that a lot of the older workers are less familiar with the technology, and a lot of them are only moderately literate, and so we have to figure out how to most effectively help them get the information that they need. So I don't think I even have a conclusion slide. Yeah, that's it. So thanks.
All right, thanks to all of our speakers. If you have any questions, you can submit them using this QA link here. It should take you to a Google form, and you can fill in the questions and to which speaker it's addressed, if any. Do we have any questions yet?
Yes, Dr. Levine, we do. So I'm just going to preface really quickly. We actually got flooded again with questions, so we probably won't be able to take all of the questions, but I will pass the questions on to Dr. Levine for her and her panel to answer. Okay, so here we go. First question, if students are interested in helping with your research, where can they go? This is to the panel. There's a button on there that you just push up.
Yeah, this one's on.
Okay, can you hear me? All right, yeah. So from my end, I love to have student volunteers. So if anyone is interested in volunteering, please reach out to me. You can find my email probably through this forum. There is also a fantastic program for undergrads here at SDSU, the Summer Undergraduate Research Program, and they have a SERP match program, so you can match with any of the faculty who are doing research that you're interested in. And there are a lot of other programs, but definitely reach out to your professors in your class and find out what kind of research they're doing. And definitely that's one way that I love to bring students in through volunteer efforts, and then sometimes that can turn into a funded project as well.
Yeah, I would say similar for me as well, and with our environmental science degree, ENVS majors have, in their senior year, 498A, 498B research experience, and so we have a sort of parade of professors who go through that class and give presentations. I would be one of them, and if you're interested, you would send me an email. Oh, but email's the best way.
Yeah, and same here. I mean, for my own research group, if you take GIS classes, remote sensing, or the watershed analysis class that I teach, that'll give you the skills to really make a even larger impact, right? So the students in, I'm just giving a shameless plug for my course in the fall, watershed analysis. So you learn how to use statistical programming to do hydrological analysis, and then you can make plots like that and make policy relevant calculations and graphs.
Okay, this one is for Dr. Natalie Mladenov, is that how I say it? How have the recent federal environmental funding cuts impacted the capital infrastructure investments made in cross-border sewage treatment?
That is a great question. What I understand from our colleagues at the EPA who have helped shepherd these funds to where they need to go is that those funds have already been allotted and so allocated. And so they're not being attacked right now. So I think those funds are safe, but you know, it is a constantly changing situation. And I think until they're spent, who knows? But my understanding is that everything is happening. The international treatment plant is currently undergoing that expansion. The engineering design is done, and I think they're starting on construction. There's also construction in Tijuana that there is a match. So for every dollar the U.S. spends, I think it's $2 matched from Mexico. Don't quote me on that, but there is funding also coming from the Mexican government, and they work very swiftly there, and they've already started working on the treatment plant, the San Antonio de los Buenos facility, and that's already underway and due to be completed soon.
Question for Dr. Biggs. How has discretion to individual areas, let me see, how has that set their measurable objectives? Are there any state-level guidelines to ensure that sustainability objectives are actually sustainable? And why do objectives vary so much across regions? Matt.
So there are guidelines, and each plan is reviewed by the Department of Water Resources. So there's multiple agencies involved in both reviewing the plans and also enforcing the plans, the different agencies. So the State Water Resources Control Board enforces the plans. They can enforce penalties for overpumping and not meeting their goals. The Department of Water Resources is reviewing and approving the plans. Many of the plans have not been approved. So they're still in the sort of revision and review phase still to this day. It's 2025. They were supposed to be done in 2020, so they're a little bit behind. And I think part of that is because there are no hard and fast rules about how sustainability targets are being set. So there's sort of an iterative process going on in the revision of these plans.
Last question. Sorry, I got your names mixed up there. This one is for Dr. Biggs. Very last question. How will California's work towards mitigating worker heat stress help spread awareness and help with heat stress in third world countries where they work longer hours, have lower wages, and worse conditions?
Yeah, that's a great question. I think, the technology optimist answer would be that by testing apps, so mobile phones are everywhere, right? And so I think one of the grassroots kinds of things that we can do is get information that's relevant for decision making in the hands of people who are directly impacted. So laws help, and information that people can directly work with is another. I also think, but then you run against the problem, okay, well, the farmers can't just stop working when it's hot every day in a place like Bangladesh because they would never work, right? Because it's always hot. And so, I think ways to more efficiently cool or make sure that there are heat protective activities that the farm workers can do, stay hydrated, we're ventilating clothing, provide shade structures. I mean, a lot of this stuff is fairly basic, but making sure that there's support from the government to provide those kinds of things, as well as the sort of grassroots in-hand information that could remind people, okay, you should probably take a rest, that kind of thing. So we're hoping that with this test case in the Imperial Valley, we can at least see how well the mobile apps work, and could be viewed as a way of potentially expanding this into other places. So, thanks.
That's all we've got. I think we're at time. Thank you so much for our panel. Thank you, everyone.
right, what a great session on faculty research and sustainability. So we heard from heat stress, farm workers in the Imperial Valley, degrading ecologies and what that means for the Tijuana watershed, but with the promise of solutions in terms of urban greening and depletion in the Central Valley groundwater, but a sustainability plan for the next 2 decades. It's time for lunch, but before we break, it's also time for another opportunity for a drawing. So we're going to be drawing 6 tickets. The first 4 are for $10 gift cards to Which Witch and a free 4-scoop sampler voucher to Hindel's Ice Cream. Let's see, oh, I accidentally picked 3. All right, so we've got 3089758. Anyone with the ticket 3089758? All right, we'll try 3089779. No one for that one. 6195210. It's going to be a long day if people aren't here. I think we should just start giving them out. Oops, that's a little more than 6. All right, let's try this one. 6195207. All right, awesome. So if you want to make your way over here, you'll get your vouchers. Anyone for 6195207? Another one, yay! Let's follow our friend here. We've got 6195218. Yay, another one still here. Thank you. And last one for the ice cream and sandwich gift card, 6195275. No one for 6195275? Right, 3089755. And 3089750. All right. That's all 6, right? All right. Awesome. So we have our drawings completed for this period. Before we break for lunch, I just wanted to give you something cool to chew on. Another fun soil sustainability fact. Just 1 teaspoon of healthy soil holds more microorganisms than all the people on our planet. So that's over 8 billion tiny life forms supporting the air, ecosystems, and the food that you'll be eating today during lunch. Soil is truly alive. Make sure to join us after lunch. We'll be convening again at 12:50 for another drawing. This one will be for 2 Mission Bay Aquatic Center class packages. And if you haven't already, be sure to complete your tabling passport so that you can receive a Shake Smart voucher. There are hundreds of those. Thank you.